All right, guys, this is day 2 of looking at increasing and decreasing functions and using the first derivative test to determine relative maxes and mins. So yesterday we learned this, that if we want to test for increasing and decreasing, we look at the first derivative. If the first derivative is greater than 0, then that tells us that f is increasing on that interval. If f prime is less than 0 for all x in a to b, then f is decreasing on that interval. And if f prime is equal to 0 for all x in an interval, then f is constant. And then we talked about the first derivative test, which tells us that if c is a critical number of a function f, and that function f is continuous on an open interval I, which contains c, if f is differentiable on the interval except possibly at that point, then that point can be classified as follows. If f prime changes from positive to negative at x equals c, then c f of c is a relative max. And if f prime changes from negative to positive at x equals c, then c f of c is a relative min of f. All right, so we're just going to do a little bit more of the same thing we did yesterday. All right, so we're given a function. This one's a piecewise function. We're going to identify where f is increasing and decreasing, identify the relative maxes and mins, justify all of our answers, and sketch the graph. All right, so first step is to take the derivative. Okay, both of these functions are differentiable. The only question would be, is it differentiable at -1? So if you plug in -1 up here, you get -1 times 2 is -2, plus 1 is -1. If you plug in -1 down here, you get +1 minus 2, which is also -1. So this function is continuous at x equals -1. So therefore, it's continuous everywhere, which means we can take the derivative. All right, so the derivative of the top part is just 2, and that's true for x is less than or equal to -1. Derivative of the bottom part is 2x, and that's true for x is greater than -1. All right, so we want to set the derivative equal to 0. So there's no point in setting the top part equal to 0 because that's never equal to 0. It's always equal to 2. But we can set the bottom part equal to 0, and that gives me x equals 0 as a critical point. And you have to make sure with piecewise that your answer to that question, that if I set these equal, my answer has to be in the domain for that piece of the function. So 0 is greater than -1, so I know x equals 0 is a critical point for this function. Okay, the other thing you need to ask yourself is the function differentiable? Okay, we were able to take the derivative, so we know both functions were differentiable, but it's possible that at x equals -1, the slopes don't agree on both sides. So I know the slope of the top part is 2, because it's always 2, but the slope on the bottom part, if I plug in -1 for x, I get -2. All right, so I would have to say that f is not differentiable at x equals -1. All right, another way to say that maybe that matches up with what we talked about yesterday is f prime is undefined. So f prime is undefined at x equals -1, so that's a critical point. F prime is equal to 0 at x equals 0, so that's a critical point. All right, so we have our two critical points. This says we don't have an interval, so we're just doing our number line. Okay, so we're going to put -1 on there. We're going to put 0 on there. We're going to plug these into f prime. So left of -1 would be -2. Anything left of -1 is going to be a positive because it's equal to +2. All right, in between, so -0.5 or -1/2. So I'd be plugging that into the bottom. Anything greater than -1 goes into the bottom. So if I plug in a -0.5, I get a negative number. All right, and then +1, again, still plugging into the bottom because that's greater than -1. And plugging in a positive for x is a positive times a positive, which is a positive. All right, so we should be able to answer this. Remember that a positive derivative means that f is increasing. Negative derivative means f is decreasing. positive derivative means f is increasing. That makes -1 a relative max and 0 a relative min. All right, so we're going to write out our justifications and then we'll sketch the graph. So f is increasing on -infinity to -1 and 0 to infinity. And we know that because f prime is greater than 0 on those intervals. F is decreasing on -1 to 0 because f prime is less than 0 on that interval. F has a relative max minimum at, all right, I forgot to do my y values. I always forget to do my y values, but you'll remember once you start writing it out. So we need to do f of -1. All right, so I'm plugging that back into the original function now. -1 goes into the top because that's where the equal sign is. So that's -2 plus 1, which is -1. And then I'm going to do f of 0. That goes into the bottom part because 0 is greater than -1. If I plug in 0, I get -2. All right, so f has a relative maximum at -1, -1. And we know that because f prime changes from positive to negative at that point. And f has a relative minimum at 0, -2 because f prime changes from negative to positive at that point. All right, so last step is to sketch our graph. Here, I'm going to use these tools since I have them available to me. That didn't work out. There we go. All right. Okay, so I know I have -1, -1, so I'm just going to plot that -1, -1. Then I have 0, -2, so 0, -2 is right there. And then my function is increasing to -1. So I'm going to start low and I'm going to increase to -1 like that. And then it decreases to +1 like that. I meant to say it decreases to 0 like that, and then it increases again. Okay, and also you know what these look like. We're increasing to -1, so that should have been my linear function right there. So I'm actually going to redraw this because I was drawing it backwards. So this is my linear function increasing up to that point like that. And then the rest of it's a parabola. So it's going to kind of decrease down to 0, hit that point, and then it's going to increase up for the rest of the time like that. All right, so again, we can create pretty nice graphs just based on increasing, decreasing, and where we know the relative max and relative mins are. You can see how this was f prime is undefined. So there's a sharp turn right there. This one is f prime's equal to 0. There's a horizontal tangent line right there. So that's kind of the difference in our two critical points that we found. All right, use the graph of f prime to identify the intervals on which the graph of f is increasing, decreasing, estimate the values of x at which the graph has a relative maximum or minimum, and justify our answers. All right, so the graph of f prime, we know that the maximums and minimums occur when f prime is equal to 0. Okay, f prime is equal to 0. Okay, and the increasing, decreasing happens in between those points where f prime is equal to 0. So first thing I'm going to do is my f prime graph. This is not the graph of f. This is f prime. I'm going to identify the places where f prime is equal to 0. There, there, and there. Okay, I would like you to be able to do it just from the graph. But if you need to, make a number line out of this. And write down where f prime is positive, where it's negative, and write where f is increasing and decreasing. And then circle and write your maxes and mins. Okay, but I'm not going to do that. Lights went out on me. All right, I'm not going to do that. I'm just going to do it straight from this graph because I think we can handle that. All right, so for part A, f is increasing on. So f is increasing when f prime is greater than 0. So that's where this graph is positive. So this graph is positive above the x-axis. So from -3 to -1. That's not -1, that's +1. And from 4 to, it's hard to tell, did they mean to stop this graph or go to infinity? Let's assume they meant to stop it. So we'll assume that that's an endpoint, and then this is an endpoint from -4 to +5. So we'll say from 4 to 5. And we know that because f prime is greater than 0 there. All right, decreasing. F is decreasing on. So now we're looking where f prime is less than 0. So I have this piece down here, -4 to -3. And this piece here in between these 2 points below the x-axis, 1 to 4. And we know that because f prime is less than 0 there. All right, part B. Find the values of x. So this is different. We don't have to find the points, and that's a good thing because we don't even know what f is. What does f look like? We could probably create a sketch from what we see right here, but as of right now, we don't have anything we can plug an x value into to get out a y value. Okay, so they're only allowed to ask you about the values of x on this part. Okay, so f has a relative max at. Okay, so I was going to write each time. So for decreasing, that's where f prime is less than 0. For maximum, that's where f prime goes from positive to negative. And then minimum is where f prime goes from negative to positive. All right, so we go from negative to positive. This is a minimum. We go from positive to negative. This is a maximum. We go from negative to positive. This is a minimum. So we only have one relative max at x equals 1. And the reason is because f prime changes from positive to negative at that point. All right, and then the last one is f has a relative min at, so x equals -3 and x equals 4. And the reason is because f prime changes from negative to positive at that point. All right, next one. So now, instead of being given a graph, they're just going to tell us a few pieces of information. F prime is greater than 0 on negative infinity to -3. F prime is less than 0 there. F prime is greater than 0 on -3 to 2. And f prime is back to less than 0 on 2 to infinity. Once again, draw out a number line if you're not feeling comfortable with this yet. Okay, I think I will draw out a number line on this one. So this number line seems to be broken up at -3 and +2. Okay, and then f prime is negative on this part, positive on this part, and back to negative there. Okay, so that tells me f is decreasing, increasing, and decreasing, which makes -3 a minimum and +2 a maximum. All right, so we've converted that information into our number line that we're comfortable with. So now let's try to answer the questions. g of x is equal to 2f of x. What is the sign of g prime of negative 1? So we just have to say positive or negative here. So take the derivative, g prime of x is equal to 2 times f prime of x. You don't have to include the constant in front when you take the derivative. Now plug in negative 1. G prime of negative 1 is equal to 2 times f prime of negative 1. Okay, we're not going to be able to write what the answer is here, but this is a positive. 2 is a positive number times a, and then we look at our number line at negative 1. We're right here in the middle, and f prime of negative 1 is a positive number. So it's a positive times a positive, which is equal to a positive. All right, I think I'll encourage y'all to try the second one on your own, see how you can do, and unpause the video and see how you did. All right, so same as last problem, we're going to take the derivative. G prime of x is equal to, we take the derivative of f, we keep the inside the same, 3x minus 5, and then we don't forget the chain rule, we multiply by 3. All right, so g prime of negative 1 is equal to f prime of, plug in negative 1 for x, you get negative 3 minus 5, which is negative 8, times 3. All right, and then f prime of negative 8, so that's over here on the left side. That is a negative number. 3 is a positive number, so it's a negative times a positive, which is a negative. All right, next thing we're going to do is start looking at this in terms of particle motion. Okay, so this is a very common example. Particle motion has shown up on the AP FRQ the last 3 or 4 years in a row. So they are very fond of testing you on this stuff. It's guaranteed to show up on the test in some way. May not be on the FRQ, but if it's not, it's definitely going to be in the multiple choice. So this is just going to use some different words. All right, we've already talked about the words when we originally did derivatives for the first time. Okay, so the words will be familiar. Those of y'all who've done some physics, you're going to be very, very familiar with the words used here. Okay, and this is just asking us to do the exact same thing. Just they're asking the question in a bit of a different way. All right, so our function s of t is equal to that, describes the motion of a particle along the line. Another word for motion is position. And another word for that is displacement. All of these words mean the same thing. All right, so this whole topic is called particle motion because we have a particle moving along a line. Could be left and right on a horizontal line, could be up and down, or it could just be along any line that's not horizontal or vertical. Okay, so this is just describing the motion of that particle, also known as the position and the displacement. All right, so the velocity function of a particle at any time t greater than 0. So velocity is the derivative of position. V of t equals s prime of t. All right, then we'll just go ahead and take our derivative. We have 2t minus 7. Okay, they wanted the velocity function, which means it should be in terms of t, and this is at any time. So we're not plugging a number in, we're just finding the function. That's what we've done here. So we're done with part A. All right, identify the time intervals where the particle is moving in a positive direction. Okay, so a positive direction is going to be when the derivative is a positive number. Okay, if the derivative is positive, the particle is moving in a positive direction. If the derivative is negative, the particle is moving in a negative direction. So we have our derivative now, our velocity. We're going to set it equal to 0. So v of t, which equals 2t minus 7, is equal to 0. So we get t is equal to 7 over 2. This is our critical number. We take our critical number, we put it on a number line. Then we take a point on the left side. So 7 over 2 is 3.5. So I'm going to go with 0 on the left side. And actually, I shouldn't have put an arrow on the end. Since we're doing particle motion, t represents time, and time is always greater than or equal to 0, as they told us in part A. So no left arrow here. Let's put a closed circle, and that's 0 right there. All right, so I'm actually not going to choose 0. Let's go with 1. So I'm going to plug in 1 for t, and a 2 minus 7 is a negative right there. All right, and then we'll go with 5 over here. 2 times 5 is 10, minus 7 is a positive. All right, so we would finish up by saying the particle is moving in a positive direction on, then we say our interval. Now, for whatever reason, with particle motion, they generally use inequality notation, whereas on our other problems, we use interval notation. Okay, it doesn't really matter. They will accept either one. I'm going to switch to inequalities, though, because that's the kind of convention for when we do particle motion. All right, so it's moving in a positive direction on t is greater than 7 over 2. And then our reason is because v of t, not v prime, not s prime. You know s prime is equal to v, so just say v of t is greater than 0 on that interval. All right, identify the interval in which the particle is moving in a negative direction. So we've already done the work for that. We just need to write out our answer. The particle is moving in a negative direction on, and then this is where the 0 is actually important. If I just left an arrow, I could have just said t is less than 7 over 2. But that would actually be wrong because t stops at 0. So you want to include that 0 less than or equal to t, which is less than 7 over 2. And we know that because v of t is less than 0 on that interval. All right, part D, identify the time or times at which the particle changes direction. Okay, well, it was moving in the negative direction for this interval, then it switched to moving in the positive direction. So those are going to occur at your critical points. They could occur at your critical points. So it won't always change direction at a critical point, but if it does, it will happen at one of those. Okay, and so it does on this one. V changes from negative to positive, so our particle changes direction at t equals 7 over 2. All right, justify. How do we know that? We know that because v of t. Okay, so this is doing like maximum minimum, right? So when we did maximum, we had to say because f prime changes from positive to negative. Had to do that in a specific way, because if it does it the other way around, it's a minimum instead. So the nice thing about changing direction is there's no maximum change or minimum change. There is, but we don't care about that in particle motion. We just care that it changed. So I don't need to say because v of t changes from negative to positive. All I have to do is say because v of t changes sign. And it doesn't matter how it changed sign. So it changes sign there. And that's our good enough for our justification. So the difference is instead of referring to the derivative, instead of saying s prime, we're using velocity. We're using v of t because that's equal to s prime. And you want to get used to doing that on these particle motion problems, using v, using acceleration once we get there to do that. All right, hopefully that went well for you. I'll see you in the next video.